Hi, I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm over at Fraunhofer with Jens Düge. I was going to talk today about how to reduce the amount of data coming from sensors at the edge. So Jens, one of the big problems as we start getting into the edge is that there's so much data that's going to be produced, particularly by vision sensors, image sensors, that there's going to have to be a lot of processing going on. But there are different ways of approaching this, right?
Yes, that's true. So the major issue when you do image processing, vision image processing on the edge, you usually don't have enough power, you don't have enough local connectivity, and you usually don't have enough time to do the processing if you want to achieve a certain goal. So our mission here in EAS is to implement efficient electronics at the edge, and my mission, the mission of my team, is to do vision on the edge within vision systems on chip.
So typically the approach in dealing with this has been to speed up the amount of processing and then be able to do some sort of partitioning of the data later on, so you discard a lot of that. That's not the most efficient way to do it though, right?
That's true. Usually all the data that is being picked up is being transferred to an external processing hardware. That can be a PC or that can be a GPU. And at the moment, the scaling of performance of image processing is done by using faster and bigger hardware, bigger GPUs and so on. But this usually doesn't solve the problem we want to tackle with our technology. The problem to condense the data in a way that it can be then processed within a very small hardware at the edge, and especially if you want to combine several sensor nodes together with each other, then of course you have to reduce it even further to meet the needs of communication channels, to extract features, to be able to combine the data from different sources.
Let's drill down into this a little bit.
Okay, sure.
So Jan, what have you got here?
So what we did in the past is to design a camera, which actually at first sight looks as like a normal traditional industrial camera. Okay. This is based upon our vision system on chip. So there is the sensor itself. It contains a focal plane with a relatively high resolution for high-speed imaging. It's a 2 megapixel sensor, but not only the pixel size, which is for high speed relatively small, it's 8 micrometers. Not only the pixel size is interesting, but also the processing that can be done in the focal plane during the readout column-wise, and then in each of the columns after the A to D conversion. So each column we have a processing element that picks up the analog data and then processes it in a digital manner.
So what you're saying here is that rather than taking the whole image, you're taking part of the image and only recording that. So instead of moving all the data up and separating out what's good from what's bad, you've just taken the good data right from the start.
Yes, exactly. So we can do this not only in the digital manner. We already start with controlling the readout of the focal plane, which is completely freely programmable. So we can control which line will be the first to read out, which are the regions of interest, and we can even combine several lines into one analog value to read it out and then to digitize the data at a certain resolution, which is also completely freely programmable. So it's possible then to not just read out everything at the highest possible resolution in terms of digital resolution, but also to at first figure out the region of interest to be interesting and then to process it at higher resolution.
So will this work with other types of data as well? You have vision, which is probably the most data coming out of any type of sensor, but can it actually work with other types of data as well?
Well, to control the complete pickup process by digital control, programmable digital control unit, application-specific instruction set processors as we use them, and then to completely freely program or control the analog to digital conversion can be transferred to every other data pickup and data processing application. So we can transfer this approach to not only normal pinned photodiode type sensors, but also to time-of-flight sensors, or to transfer it to completely different data acquisition and processing applications.
This also is a relatively fast way of doing it, right? It should run faster simply because you're moving around less data.
Yes. We move around only the data we, in the beginning, figure out to be interesting. So that means if you want to follow the face of a person, or if you want to track particles, then you just read out the particles themselves, which you determine by, let's say, thresholding. And then you have to process just the little regions of interest, not just one, can be hundreds, afterwards, after the compression and after the analog to digital conversion of these very small regions of interest.
This is also because you're focusing on the data right up front, this also can potentially reduce the cost that you have of actually running the system too, right?
Exactly. So if you want to achieve speeds above 1 kilohertz, let's say 10 kilohertz frame rate, and you want to read out standard image sensors at this frame rate, let's say 2 megapixel sensor at this frame rate, you need quite some digital interfacing. And this always has to be combined with relatively large FPGAs, if it's a standard industrial camera. And usually this is a big limitation to scaling the image sensor speed in certain applications. So if you can reduce the data, you can still run at high speeds, at high frame rates, kilohertz range, and still don't have to sacrifice for this interfacing issue.
This goes against the way that we've been building devices for years, right? Because we've been getting faster and faster, more and more resolution, bringing the entire picture. This is a completely different way of looking at the problem.
Yes, exactly. This is a completely way of doing this, but we are not just picking up features. We can still transfer real image data, but we at first choose what's interesting for us, but relatively small and relatively simple features, thresholds or edges or so on.
So there's one more piece here, which is that you want to be able to take these designs and reuse them as much as possible, right? How do you do that?
That's true. We do this by using programmable CPUs, application-specific instruction set processors, which are programmed with a standard programming language, very well known. This is done with Python, with embedded assembler. So whenever you need very high, very hardware, close to hardware processing, then of course you implement it in assembler. But besides of this, it's Python, which of course increases the development speed for engineers to get into this software development. And we have 3 processors on the sensor. One is to control the focal plane, because this is the first step to reduce the data. Then the second one to control the processing elements. And the third one to do all the communication, because this is also a very interesting question. How do we get all the data, maybe synchronization data, and how to transfer the data, which might be triggers or synchronization, as I said, or any kind of other metadata out of the sensor besides the data stream itself. So this is done by general purpose IOs that can be in software connected to any of the devices on the sensor doing image capture or doing data processing.
So reality here is that you can take in as much data as you want with this model, unlimited as much as you want to, depending upon what your priorities are.
Yes, exactly. That's exactly the point here. We do reduce the data by supplying software components to customers to be able to use this approach for their application. And if there's there are customers that are not don't want to deal with the sensor itself, they still can use the possibility by using software libraries to get on top and then to use their traditional ways of processing an external hardware, but not on full frames, but on reduced regions of interest.
And there are some upstream savings in here as well, right? So you've got you reduce your latency, you have a lower need for bandwidth because you're not moving as much data, less power in order to be able to run this whole thing. So basically, this is an entire system level approach.
Exactly. So just to give you a short example, if you just want to track one single spot, one single, let's say, melt pot within a laser production, laser welding unit, then of course this spot has a certain features like size, like area, number of pixels involved, and this can be read out. This is located as let's say in the center of the focal plane. Then you can read out only the pixels, the lines that are containing this grayscale data. But on the other hand, if you would read out the whole lines, you still have some data, some dark pixels you don't want to read out. So there is another step of compression. You can read out the data afterwards only of the processing elements involved. So this is another second step to compress the data, because the regions of interest are not just compressed in Y, but also in X range.
Jens Düge, thanks for a really interesting talk on how we're going to tackle some of the problems at the edge.
Thank you for the interesting questions.